Greetings, everyone. Hope you're doing well today. Thank you for coming to my talk. My name is Darren Irwin, and I'll be speaking about how assortative mating and low hybrid fitness influence this very mysterious thing we all call reproductive isolation. I want to thank Leo and Al for inviting me and for organizing this symposium. So reproductive isolation is usually thought of as two distinct types. Prezygotic isolation, those are factors that prevent hybridization between two species or populations, and postzygotic isolation. Those are factors that cause low fitness of hybrids. And Ernst Mayr emphasized the difference between these when he wrote, isolating mechanisms clearly fall into two very different classes, pre-mating and post-mating mechanisms. There is a fundamental difference between the two types. Pre-mating mechanisms prevent wastage of gametes, and so are highly susceptible for improvement by natural selection. Post-mating mechanisms do not prevent wastage of gametes, and their improvement by natural selection is indirect. What Mayr is referring to there is this process of reinforcement, by which some postzygotic isolation, low fitness of hybrids, leads to selection for factors that prevent hybridization. So there's been much written about this process that sort of puts postzygotic isolation as the driver of speciation. Yet, much of the literature presents prezygotic isolation via mate choice as often being the most important of these two. And so here are some quotes that I've selected, and these are all from people I really admire. They're all, really impressive people in the field, as well as myself there. And I just included one for me to show that I've thought this way in the past. So just some quotes here. Reproductive isolation in birds will often depend on prezygotic mechanisms. Or speciation in birds proceeds with the evolution of behavioral barriers to interbreeding. Post-mating isolation usually evolves much later. Or pre-mating isolation can play an important role in the early stages of speciation, allowing for the accumulation of other isolating mechanisms. So sort of we think that assortative mating is really influencing prezygotic isolation, and it's thought to be very important, whereas postzygotic isolation is often said to be unimportant early in speciation. And this is because of the observation that hybrids often appear to be viable and fertile. But we can note here that there are various ways that hybrids could have somewhat lower fitness that would be very hard to detect using these ways of looking at it. Speciation is often studied by using secondary contact zones, where two species come together in nature and we can observe their interactions. Often hybrid zones are formed, and here's an empirical example that we've studied, just two species that have a narrow hybrid zone between them. To explain such situations, various people, including Nick Barton and colleagues, have developed very powerful and useful theory that we've used a lot to relate the Klein width to the dispersal distance of individuals and the strength of selection against heterozygotes. And the idea is that low fitness of hybrids keeps that region narrow, and you have net gene flow into the zone from outside. So the more reproductive isolation you have, the narrower zone you have. Now, there's a curious thing about this theory, and that is that it assumes no assortative mating, and this is largely for reasons of tractability of the math. But there's sort of a conundrum here that a lot of the literature presents pre-mating isolation as really key and important, yet hybrid zone Klein theory assumes random mating. So I wanted to kind of tackle this by simulating hybrid zones that have assortative mating. And so I developed a model that I call the Hsam model, hybrid zone with assortative mating. It's written in R. It's an agent-based model of sexual diploid individuals. The starting point is that two populations have just come into contact. Individuals have three unlinked loci in the examples that I'll show you here, each with two alleles, a 0 allele and a 1 allele. And these additively contribute to a trait T ranging from 0 to 1. The starting populations are fixed for different alleles, 0 here and 1 here. There are non-overlapping generations with cycles of mating, reproduction, survival to adulthood, and dispersal. And I don't have time in 12 minutes to go into all the details of the model, but I want to talk about how assortative mating and low hybrid fitness are specified. So with assortative mating, we have females randomly encountering males that are close to them on the landscape, and they can accept or reject a male. If they reject one, they encounter another. And you can switch the sexes here. It's not important which is the male and which is the female in this case. The probability of acceptance depends on the difference between the male and the female traits. So if they perfectly match, then her probability of accepting that male is 1 all the time. But if they're different, the sort of attraction declines according to a Gaussian curve. And we express the strength of assortative mating as the ratio of the attraction to their own form versus a full heterospecific form. So a strength of assortative mating, SAM equals 10, means that they're 10 times greater attraction for their own species than the other species, quite strong. Low hybrid fitness is defined using heterozygote disadvantage. So W-hyb shows the fitness of hybrids, F1 hybrids that are full heterozygotes. Partial heterozygotes have only a partial loss of fitness, according to the equation on the right. We also have a model with epistasis that produces similar results, at least in terms of what I'm going to show you today. So here we have an example where there's 10 times preference for the same type, and there's no predefined low hybrid fitness. So W-hyb equals 1, the same as the starting species. We have a one-dimensional range here, location across the bottom, and across the vertical axis, we have hybrid index. So we have individuals of the first population with hybrid index 0, second population hybrid index 1. Let's play this. And you're seeing not much interbreeding. Oh, there were some F1 hybrids and some back crosses, but not very much because they really prefer their own. But as we go further and further in the generations, you're seeing hybrids generally build up in these back crossers and F2s and so forth. And what's happening is a full continuum between the two species is developing. So despite this quite strong assortative mating, it's not preventing this genetic bridge from forming between the species. And why is this? Well, if there's assortative mating, intermediates are attracted to similar intermediates. To specify otherwise would not be assortative mating. It would be something more complicated, where hybrids have some different behavior from the parental species. So if there are enough intermediates around, then everyone has someone to mate with, and a continuous hybrid zone develops. So here in the purple line, we see over the generations, the assortative mating zone width kind of goes up, but then it reaches a stable point. But it's a wider zone than a simulation with a small reduction in hybrid fitness. So just a 10% lower hybrid fitness results in the green line for zone width. So the one take-home message is that a small reduction in hybrid fitness keeps the zone narrower than strong assortative mating does. But the assortative mating one is keeping the zone narrower than pure neutrality does. That's the gray line. Now, why is this? There is a full genetic continuum, so why doesn't the zone get wider? Well, we hypothesize that the assortative mating causes a rare mating type disadvantage. And I'll explain in a bit what this means. But let's test this idea by tracking fitnesses using the Hsam sim model. And this is a collaboration with Dolph Schluter. We have a manuscript on bioRxiv about this. It's a non-spatial version of this model that also incorporates ecological differentiation. So let me walk you through this chart. This is summarizing a simulation with 1,000 times preference for the same type. So SAM equals 1,000, strong assortative mating, but no predefined reduction in hybrid fitness. W-hyb equals 1. Here on the top graph, we have the hybrid index. That's like the trait value. And so we have 0 and 1 are the starting species. And the darkness is the number of individuals at that hybrid index at that generation time. And you see as generations go by, left to right, there's quite a stable situation. There's these two species persisting, despite, in the little gray bars, there is production of rare hybrids. Now, why aren't those hybrids building up and forming that nice, sort of big continuum between the species? Well, it's because their realized fitness, measured and graphed on the bottom, is lower than the parental forms. So the fitness of the starting genotypes is shown in those lines there. It's about 1, but the realized fitness of the hybrids is just about 70% or 0.7. And this is an emergent property of assortative mating. Male hybrids have few mates because they're unlikely to encounter a female hybrid. And they're more likely to encounter a female of the parental species that are not finding them attractive. So this keeps the fitness of hybrids low. So choice-based assortative mating can be a form of postzygotic isolation. And here we have a case on the right where there's just a little bit less assortative mating in this case on the right. And what you're seeing here is a similar starting point to the model on the left, but hybrids gradually build up in this case because the assortative mating is a little bit less, to the point where hybrids are common enough that they can find other mates that like them. And then the frequencies and the frequency-dependent selection sort of flips around. And the hybrids then have high fitness and the original parental forms don't. Now, this is not a new phenomenon. It's been discussed, for example, this paper, Otto et al. Have discussed this kind of phenomenon of rare mating type disadvantage and how assortative mating can induce this. But it hasn't been really incorporated broadly into hybrid zone theory or speciation theory. But so assortative mating affects both pre- and postzygotic isolation. Now, might hybrid fitness also affect both of those? Let's explore this idea by looking at the spatial version of the Hsam model. So here we have a case with no mate preferences, no assortative mating, but hybrids have 90% fitness, so a 10% reduction in fitness. If we run this model forward, the blue line is just kind of a Klein fit through this, through the data there. You'll see that this is a very, it bounces around, but it's mostly a stable situation of a narrow hybrid zone caused by this 10% reduction in fitness. But if we think about what's happening here, the zone and the low fitness of hybrids is actually preventing full sympatry of the two species. And this results in segregation, spatial segregation of the two species, which can be viewed as a form of prezygotic isolation. So there's sort of this emerging view, the idea that postzygotic isolation is not important. I think I'm advocating towards sort of clearing that out. And instead, we can view assortative mating having an influence on both prezygotic and postzygotic isolation. And many other types of things can also reduce the fitness of hybrids. And so postzygotic isolation is likely very important in speciation. And postzygotic isolation, through this geographic separation effect, can in fact create a sort of prezygotic isolation. It can also do it through the process of reinforcement. So some take-home messages are that the characteristics and fitnesses of hybrids are crucial in determining the future of a hybrid zone. And pre- and postzygotic isolation are often not separable phenomena. Mating traits affect both. So with that, I'd like to thank you for your attendance. I really look forward to the other talks in this symposium that I think will be excellent. And to learn more about any of these things, you can see these two papers or go to the GitHub site if you're into actually running code yourself. Thank you very much.